Welcome back to G Fun Facts Online. Today we are not just talking about a scientific improvement, we are talking about what chemists have called the holy grail of catalysis for over a century. We are diving deep into the energy sector's most significant recent disruption, the conversion of methane into liquid methanol in a single step, at ambient temperature. This is a story about how we stop wasting one of the planet's most abundant energy sources, and how we might finally kill the massive, pollution-belching refineries of the past. Let's start with the problem, which is often called the methane paradox. We live on a planet absolutely awash in methane. It bubbles up from permafrost. It leaks from oil wells. It is generated by livestock, and it makes up the vast majority of our natural gas reserves. Methane is the simplest hydrocarbon, CH4. It packs more energy per carbon atom than any other fossil fuel. But here is the paradox. Despite its potential, it is a nightmare to handle. Unlike oil, which you can just pour into a barrel, methane is a gas at room temperature. To transport it, you have to compress it under immense pressure or freeze it down to -162 degrees Celsius to turn it into liquefied natural gas, or LNG. This logistical nightmare leads to a tragic economic reality. In remote oil fields, it is often cheaper for companies to simply burn the methane as waste, a process called flaring, rather than building the expensive infrastructure to capture and transport it. This wastes a valuable resource and pumps millions of tons of CO2 into the atmosphere. Even worse, if that methane leaks unburned, it acts as a greenhouse gas 84 times more potent than carbon dioxide over a 20-year period. For decades, the dream has been simple. What if we could just add an oxygen atom to methane? If you take CH4 and add oxygen, you get CH3OH methanol. Methanol is liquid at room temperature. It is stable, energy-dense, and can be stored in standard tanks and transported by normal trucks. It is also a feedstock for plastics and paints. This direct conversion is the holy grail. It sounds easy, but nature fights it tooth and nail. Methane is thermodynamically stubborn. Its symmetrical, tetrahedral structure and strong nonpolar CH bonds make it incredibly inert. It does not want to react. To make it react, you typically have to hit it with a sledgehammer of heat and pressure. But here is the catch. Once you do get it to react, the product, methanol, is even more reactive than the methane. So, the moment you form methanol, it tends to keep oxidizing all the way to carbon dioxide. You end up burning your fuel instead of making it. Because of this difficulty, the industry currently uses a brute force method called steam methane reforming. It is a massive, two-step beast. First, you blast methane with steam at 900 degrees Celsius and high pressure to break it into syngas. Then, you recompress that syngas to make methanol. This process is only efficient at gigantic scales, requiring billion-dollar refineries. You cannot build a steam reforming plant at a small remote oil well, so the methane continues to be flared. But that brings us to the breakthrough. In late 2024 and 2025, a series of papers shattered this paradigm. We have unlocked direct methane to methanol, or DMTM, at ambient conditions. This bypasses the syngas route entirely. The core scientific victory here is breaking the selectivity conversion trade-off. In the past, if you had high conversion, you burned everything to CO2. If you had high selectivity, you only converted a tiny fraction of the gas. The new catalysts break this seesaw by creating a protected active site where methane is activated, oxygenated, and immediately released before it burns. Let's break down the three technology pillars driving this, starting with the thermo-catalytic breakthrough from Brookhaven National Laboratory. In August 2024, they published a paper detailing a catalyst that achieves 100% selectivity for methanol at temperatures lower than what you need to brew a cup of tea, around 75 degrees Celsius. The catalyst is a ternary system: palladium, cerium oxide, and the secret sauce, interfacial carbon. Now, usually, carbon on a catalyst is seen as coke, a gunk that ruins the reaction. But the Brookhaven team engineered an atom-thin layer of carbon between the palladium metal and the cerium oxide support. This wasn't pollution, it was a bridge. This interfacial carbon modulates the electronic properties of the palladium. The mechanism works like a pressure cooker, but at mild pressure. It involves a solid catalyst, liquid hydrogen peroxide, and gaseous methane. When methane hits the surface, the catalyst activates the CH bond just enough to let an oxygen species slip in. Crucially, the water in the reactor helps wash the methanol off the surface immediately. This rapid desorption is why they get 100% selectivity. The methanol never stays on the hot surface long enough to degrade. The second pillar is the photo-catalytic approach from the University of Manchester. While Brookhaven used heat, Manchester used light. Their work focuses on metal organic frameworks, or MOFs. Think of MOFs as crystalline sponges, materials with such vast internal surface areas that a single gram has the surface area of a football field. The Manchester team decided to mimic biology. Nature already knows how to do this. Bacteria called methanotrophs use an enzyme to eat methane. The researchers built a MOF that mimics this enzyme, using ruthenium as an antenna to absorb visible sunlight and iron as the active site. Inside the tiny pores of this MOF, they engineered mono-iron hydroxyl sites. When sunlight hits the ruthenium, it excites an electron, which activates the iron site to split oxygen and insert it into the methane. Because this happens inside the confined pores of the MOF, the methane is held in a specific orientation, like a key in a lock. This prevents chaotic reactions. This process runs at room temperature, 25 degrees Celsius, driven entirely by visible light. It is effectively artificial photosynthesis. Instead of plants turning CO2 into sugar, we are turning methane into liquid fuel using the sun. The third pillar is perhaps the most futuristic, the plasma frontier, pioneered by the University of Liverpool. This uses non-thermal plasma. Now usually, plasma is incredibly hot, like the sun, but in non-thermal plasma, the electrons are super hot, thousands of degrees, but the heavy ions and gas molecules stay at room temperature. You can touch this plasma with your hand. It feels like a breeze, but chemically, it is a thunderstorm. The Liverpool team combined this plasma with a nickel-cobalt catalyst. The high-energy electrons smash apart the stubborn CH bonds of methane without heating the gas, creating methyl radicals at room temperature. The catalyst then guides these radicals to form methanol. The killer feature here is that it is electrified in an instant. Thermal plants take days to heat up. Plasma reactors turn on and off like a light bulb. This makes them the perfect partner for renewable energy. When a wind farm is producing excess electricity at night, instead of wasting it, you dump that power into a plasma reactor to convert biogas into methanol. It acts as a chemical battery, storing electricity as liquid fuel. So what does this mean for the economy? It signals the death of the mega-refinery. The transition from high-temperature, high-pressure systems to ambient, modular systems fundamentally breaks the economics of petrochemicals. We are looking at the valorization of stranded gas. The World Bank estimates over 140 billion cubic meters of gas are flared annually. That is enough to power sub-Saharan Africa. With these new technologies, you don't need a $2 billion plant and a pipeline. You can put a $500,000 reactor in a shipping container, put it on a truck, drive it to a remote well in North Dakota, hook it up, and start filling a tanker with methanol immediately. This unlocks billions of dollars from what is currently treated as garbage. This also enables the methanol economy. Major shipping companies like Maersk are already ordering methanol-powered ships to reduce emissions. Ambient methanol lowers the cost of this fuel significantly. It also serves as a hydrogen carrier. Since hydrogen is notoriously hard to store, transporting methanol, which is 12.6% hydrogen by weight, is actually a more efficient way to move hydrogen around. Environmentally, this closes the carbon loop. Methane has a global warming potential of 84. Every molecule we convert to methanol is one less molecule heating the planet. If we apply this to biogas from farms and landfills, we can achieve carbon-negative fuels. We take carbon from the air via plants, turn it into methane, catch it, and lock it into methanol, which can be used to make plastics. That is a net reduction in atmospheric carbon. However, we have to remain grounded. There are engineering challenges. The first is stability. Real-world natural gas is dirty. It contains sulfur, which poisons catalysts like palladium and iron. The Brookhaven catalyst needs to prove it can survive this, or we need expensive pre-cleaning. There is also the issue of leaching, where the active metal slowly dissolves into the liquid methanol over months, ruining the catalyst. And for the Manchester photo-catalyst, the challenge is light penetration. It is hard to get sunlight into a massive industrial tank. Looking at the roadmap, we expect pilot plants and containerized units to appear at test sites between 2025 and 2027. By 2030, we could see the first commercial licensing of turnkey methanol units for the oil and gas industry. To conclude, the discovery of ambient, single-step methane to methanol catalysts is a watershed moment. We are moving from the age of brute force chemistry, beating molecules with fire, to the age of precision catalysis. This technology solves energy security by unlocking stranded gas, fights climate change by stopping flaring, and provides a bridge to a sustainable future. The flare stacks that dot our horizon may finally go dark, replaced by silent reactors producing the liquid fuel of the future. Thanks for listening to this deep dive on Fun Facts Online.